This is a video guide for an extra credit assignment for suitability, and in this extra credit we're going to be utilizing the suitability model, specifically a weighted model. First we'll run it as unweighted and then we'll actually weight it. And the original data comes from Tufts University, from their GIS program, from their data lab, and it was developed in 2017. So once we download the data, I'll have a link to the data from the video itself. It comes organized in MXD and also pre-processed data. So if we take a look here, we can see that we have a steady area boundary, wind, land cover. There's also some infrastructure, which is the Great Wall and power lines. And it's important to note that Tufts has deemed this proprietary data, so we're only going to use it specifically for this tutorial. We're not going to actually distribute it any farther or use it for any other purposes. And let's take a look. There was one other item there that we have. So in addition to Great Wall and power lines, we also have elevation. So this is going to be a SRTM DEM. We're also going to have a land cover, which we're not really going to use, but we can use it just to preview. We'll also have wind data. So if we take a look at the wind data, this is basically a wind potential within the study area. Okay, so when you download the data, you'll have this all set up. We can just go ahead and open the default start map. That's fine. You could also just run the data into your own MXD separate of the start map. There's nothing magical about this particular MXD. So as we open it up, we are going to just take a quick look at what we have here. So the study area is north of Beijing, and what we want to find out through this process, through the suitability process, is contiguous areas of land that would be suitable for developing essentially a wind farm, or the power supply for a wind farm. So it needs to meet several different criteria, and we're going to go through those real quickly here. So this is a rundown of all the things that we're going to do. And to get started, let's go through the suitability itself. So this is an energy storage facility north of Beijing, and the criteria here is going to be it needs to be in a high wind area. It needs to be on land that's fairly level. It should be close to existing transmission lines. And the site should not interfere with the Great Wall. So we don't want to be able to see any industrial infrastructure in the way of a view from the Great Wall. Okay, so we're going to utilize the pre-processed data. So it's nice and cleaned up already. If we were to do this outside of the tutorial, we would need to organize our data, get it all ready to go beforehand. But they've done that at Tufts Lab for us, so this could be relatively easy to focus in on the analysis steps themselves. So here we have power lines in the Great Wall. We also have a DEM SRTM, and importantly, this is a 90-meter product, I believe, so everything in this assignment is going to be at 90 meters. We have, what else do we have? We have wind power itself from the National Renewable Energy Lab. And so these are the four things that we're going to process. So we need to figure out distances from the Great Wall, distances from power lines. We need to calculate our wind power, and we also need to deal with elevation. And those fit these criteria, these four criteria right here. So our data fits the criteria. For our analysis steps, what we're going to do is we're going to look at wind, and we're going to be selecting some attributes from the wind layer. We're then going to be deriving slope, and once we have slope derived, we're going to pull out areas that are relatively flat. We're going to derive distances from transmission lines, and then we're also going to derive distances from the Great Wall. And each time we do this, we're going to have to reclass into essentially a 1 to 5 preference listing or criteria. And then we'll go into 2 final runs of suitability. The first one will be unweighted and the second one will be weighted, and we'll see the difference between the two. We also need to establish our processing environment, so we'll work through that together early on. And we're also going to do our analysis steps one by one throughout the layers. So here we can see power lines. We're going to do Great Wall. We're going to do elevation. And then we're going to do our final run. We're going to have no weights. And then our second run is going to be 4 different weights. So the first one is it has to be close to high wind. That's a very important factor. So we're going to weight that very high, which is going to be at 50%. The distance to power lines would be the next important factor, and that's going to be at 25%. Distance from Great Wall is less important at 12.5%. And slope is less important, weight at 12.5%. Remember, this is a criteria that's been set up by Tufts Lab. If you were doing a similar suitability project for, say, a different geography and for different issues, you might have very different criteria based on the deliberative process around your project. And finally, at the very end, what we'll do is we'll have float values that come through our process, and we want to bring those into an integer type. And we can just run, through spatial analyst tools, we can run a integer tool. And at the end, we should be able to get a result that's similar to what we're looking for as suitability for our wind power station. Okay, let's go ahead and get started. So I'm just going to minimize that. And the first thing I want to do is kind of clean up this MXD before we get started. So I really don't need the physical reference anymore, so I'm just going to click off that, and boundary in places is going to go away. I'm not really going to use the land cover, so I'm just going to actually remove that altogether. We're going to be working with wind, okay, power lines, the Great Wall, and then of course we also have SRTM data, which I need to make active here. Let me show you what that looks like real fast. So we can see that for our SRTM we have low values that are dark, so it's relatively flat by Beijing, and then as we go into higher elevations. But what we're really looking for are areas that are relatively flat. So it's not so much the elevation, it's actually the slope, and we'll calculate slope in just a little bit. Okay, so the first thing we need to do to get started is we're going to set up our working environment. And when we're doing a lot of geoprocessing, especially with suitability, we want to establish this thing called a working environment. And the first thing we want to do under geoprocessing is go to geoprocessing options and make sure that we have background processing checked off. So I'm not going to enable this. I'm going to click this off as if it's already on. It should look just like this. And that's going to allow us to see the processing in the foreground so we know exactly what's happening. We also want to set up an environment. So we're going to go to Geoprocessing Environments, and here we're going to actually set up a workspace. So we go down to Workspace, and our current workspace is just in default geodatabase. We want to actually point it to our working folder. So we will go, I have this sitting on the desktop right now. So it's this wind farm suitability exercise. That's what I'll set it up as, my workspace. Okay. And then, so I'm pointing to the folder itself. And then for the Scratch workspace, that's going to be inside. That's where everything's going to be sent to as we're processing. So I want that to actually be in pre-processed data. So I'm going to come in here and set this up here. And I'm just going to call it TMP for temp. Okay, and I'll point it to temp. So that's where everything's going to end up. If I'm looking for my processing files, that's where it's going to go. Okay, so once that's done, then we can say OK. The other thing we want to do is go back to environments, and under the processing extent, we want to set it to our study area, and we also want to set it to a cell size too. So in this case, what we want to do is the extent is going to be our SRTM base, DEM base. Okay, and the roster itself, all the parameters of the roster are going to also be set to SRTM Beijing. And we say, okay, this is just giving us kind of a common coordinate space and working space by which all our processing will adhere. So we go ahead and say okay. So once that's established, then we want to go ahead and just say File, Save, because we're saving the MXD that's going to save that working environment. And we might also want to just keep open as we're working along the actual study area. So we're going to be processing within this space. This is all we care about. We're not actually going to process on the outside of this. All right, so once we have all that set up, let's go ahead and, for our second step, let's work on wind. So the criteria on wind is anything that has a grid code value of greater than or equal to 3 is going to be considered of interest or suitable. So we need to do a SQL, because this is actually, if we look into the open attribute table, these are polygons. Okay, so this particular data set is coming in as a polygon, contents back. All right, so if I put this on top, these, they look like cells, but they're not. They're actually just polygons. We can go ahead and select by SQL. So we'll do select by attributes, and we put in wind, and the grid code here is going to be greater than or equal to 3. Okay, say apply, okay. And then we want to send this out. So when we go to data, export the data, it should see the path. Let's see if it does. So it goes, yeah, there's our temp folder. We can see it in the path there. And remember, no spaces, no odd characters. So here we'll just call this, I'll just call it wind 3 for now. So it's my grid code 3 value, and I'll say OK. There's going to be a lot of intermediate steps through this whole process, so there's going to be a lot of files that we don't actually need beyond an intermediate step. So don't worry about the naming until I actually call out that the naming is very important. So we'll clear selected features here. And at this point, what we want to do is figure out distances from this area. So this is, if we are within this grid code, which is 3 or greater, then that's considered to be suitable. And we want to create distances from these areas. So as we get farther away from these areas, that's considered to be less suitability, or it's less preferred. So if we're actually inside, that's really great. If we're slightly outside, that's okay. And if we're very far away, that's not okay. And so to do that, we first have to set up a distance. So that's going to be what's called a Euclidean distance. And to run that, what we'll do is go into our Arc Toolbox. We're going to be doing this several times over, so once we do it, you'll know where it's located. Okay, so we're going to want to go into Spatial Analyst Tools, and we're dealing with distances. So go to Distance, and Euclidean distance is what we're looking for. So the input here is going to be Win3, and the output roster should be going to our temp folder, and we can just let the name be what it's going to be. And we can see that we have an output cell size of 90. That's exactly what we want, because it's pulling the cell size from our environment, our working environment that we established early on from SRT and Beijing. Okay, so let's go ahead and run this and say OK. And what it's going to do, it's going to give us back cells that are 90 meters that show distance. So we can come in here and put this guy on top. And what we have now is distances in meters from wind 3. So we can see a lot of this is going to be 0, right? So let's click off wind. And so if I put my information tool up here, let's do that. It's going to be right up here. I should just have like a 0. So the class value here is 0 because it's within. But when I get out down here, we can see our class values are quite a bit different. I'm sorry, I shouldn't say class value. The pixel value. The pixel value is the distance itself. So this is very far away. So when I get here, my pixel value is 0 because I'm within. And then as I come along, we can see that some of these are now going to be a little bit farther away. All right, so let's go into actually reclassifying this. So now we have the distances, but what we really want to do is we want to reclass this into a 1 to 5 ranking. So 1s are going to be very low suitability, and that's going to be this stuff down on the bottom that's very far away. And the very high suitability, the 5s, are going to be both within and very close to our wind grid code of 3 or higher. So what we want to do here is we want to do what's called a reclass. And we're going to go into our toolbox, find our reclass tool, and click on reclassify. And our input raster is going to be our wind. And what we can see our values over here, and we're going to reclass these values. And we're going to always be reclassing on the field's going to be value throughout the whole process. So I click on classify. And I want to go to equal interval. So we're going to set up equal intervals. Let's make the classes 5 because we have 1 to 5. And we're going to actually use not the default here, but we're going to force this. So our breaks are going to be at 2,000, 4,000, 6,000, and 8,000 for wind. So the first one's 2,000. Second one is going to be 4,000. Next one's going to be 6,000. Then we got 8,000. And then we'll just leave the top value sitting there. So we can see that we're capturing most of, when we look at the histogram, we got most of our values within those breaks right there. Let me change this to 8,000. Yep. Okay, there's a few that are left over, but those are going to be so far away that they're just deemed completely unsuitable. So we'll be okay. So what we have now is we have 0 to 2,000. That's the class that we really want. And the problem is it's stuck in 1s. And we want to reverse this. So we want a 5 to be 0 to 2,000 because that's the real suitable stuff. And we can just simply click on reverse new values for that. And we can see now we have 5 sitting on top. So that's exactly what we want. And here's where the name is important. So if we come along here and go to our temp folder, we want to actually name this something meaningful. So in this case, it's going to be reclass underscore, I'm going to make it capital wind, W-I-N-D. Okay, and I'll just save that. And here it is. It's classed 1 to 5. It's got a color scheme that doesn't really help us out. So what we can do is we can just simply go to properties and stretch it and get a green to a red ramp. So here we go. The problem here is that we have a value of 5 that's red, and 5s are really good. So what we can do is invert this to get our green. So reds are, we don't want that. We only want the greens. So we say apply. Okay. This just gives us a visually a little bit more understanding of what's going on. So if we were just using this one criteria, the greens would be where we would cite this wind energy facility. because the greens are highly suitable. So I'm going to save it at this point. We want to save each time we actually finish a process because we can get a lot of crashes when we're processing in GIS because it has to think through all these cells. All right, so this is an intermediate file, so I don't really need that anymore. So it's just a processing file, our Euclidean distance. So I'm going to remove that, and we're going to move on to the next one. I'm also going to remove wind. Okay, so the next one is going to be power lines. So with power lines, if we put power lines on top, we can see that they are close to Beijing, or at least down in the south, and that makes sense because that's where most of the population is. So ideally, we want to be somewhat close to that infrastructure. There's no reason to stick a facility way out in the middle of nowhere where it doesn't have any connectivity with infrastructure. So let's go ahead and run a distance on these power lines. And again, if we open the attribute table, we can see that these are polylines. And let's run that. And there is a hiccup with this, which I'm going to kind of explain and how we can work around that. So let's run into the mistake first, and then we'll solve it together. So if we go to our toolbox, we want to do the same process. So we're going to go to distance, and we're going to set up a Euclidean distance. And here we're going to input our power lines. And 90, it's going to go to the right place. And we say OK. And what happens here is that we actually that worked out fine. So I guess it happens on the wall. So when I get there, I'll explain the problem. So this looks good. So we can see that if we're close, we're going to be yellows. If we're far away, we're going to be blues. So we're going to do the same process again, using Euclidean distance for power lines. So what we need to do is go into our toolbox. We're going to go to reclass, reclassify, power lines in, value, same difference. We're going to do this all over again. So we go to classify, and we're going to go to equal interval. We're going to go to 5 classes. And our breaks are going to be slightly different this time around. So, come on, I'm going to say OK to get it to kick in. So let's go back to classify. So it's at 5 breaks. That's great. So our breaks now are going to be at 1,000. And then the next one's going to be at 3,000. So if we get something within 1,000 feet, or 1,000 meters, that's considered to be highly suitable. And then we go to 5,000, and then 8,000. Anything above 8,000 is just going to not even be suitable. So we catch actually a very small part of the histogram. So we're really interested in a pretty select amount within the larger data set here for Euclidean distance. And I have it on manual. It's either equal interval or manual is going to be fine because we're setting up these breaks over here ourselves. So once again, we need to reverse this. So we're going to stick the 5s on top. Okay. And we say OK. And that's what it's going to be called. All right. So there it is. We can see that we have a lot of area that's the purple that is completely unsuitable. And then as we get close, it looks like our blues are what we want. So let's go in and just put a stretch on this. All right, so our highs in this case, again, we're going to invert it so we can see greens. I'm going to get rid of my Euclidean distance. And that's what it should look like. So anywhere in the green is considered suitable. So now if we click on, click off, we can see that there's some areas over here that are going to be suitable, and then also in this area. The rest of it between these two layers isn't particularly suitable. So this Euclidean distance reclass for power lines really puts a hold on the first wind reclass. All right. So what we want to do now is we want to Actually, I should have renamed this. I should have called this reclass power lines, but I'm just going to go ahead and change it here in the table of contents. So when we do get to the actual suitability, we know what we're doing with it. So this is going to be called reclass power lines. Go ahead and say save. All right, so now we're going to move on. So get power lines out of here. I'm going to actually, let's see, I'll stick power lines down the bottom here. Now we're going to work on Great Wall, which is a little bit of an issue. So if we click on Great Wall, let's run distance to get our surface. So I'm going to go to Euclidean distance, going to input our wall. Goes to 90, goes into our temp folder, and I'll show you what's happening here. Yeah. So here what's happening is that we can see right down at the bottom, we're getting a drop off of our Euclidean proximity. It just kind of falls off, and it's not the pattern that we expect. We would expect to see, as we're moving away towards the bottom, that we would get into our magenta colors and maybe even into blues. So one way to work around this is actually to change the file type from a polyline. So if we go to Great Wall Beijing, open the attribute table, we can see that it's a polyline. What we can do is just turn that. If you might not run into this problem, but if you do, we can just simply switch this around to a raster. So under conversion tools, we can go to raster from a polyline. So here I'm going to input the feature as Great Wall, and it doesn't really matter what the value field is. I'll just make it. I'll make it the name. And the cell size, though, you're going to have to do on your own. So here for the cell size, we want to have a cell size that's small because we want to keep fidelity with the original polyline. So in this case, if we make it too small, it takes forever to run it. But I'm going to pause the video. I'm going to try a cell size of 5. So it's going to be 5 meters. And I'm just going to go ahead and say OK. And I'll let you know how long this takes. Okay, so that took about 1.5 minutes to run. That's doable. So I'm just going to go ahead and proceed here. So if I close and take a look, what I have now is I just have a polyline that has been turned into a raster. And if let's do this, let's zoom in there and take a look at what we got. So I'm just going to get real close. And if I make this yellow, stick him on top. So it's going to give us a little bit different processing result, but I don't think it's going to be significant. So we're going to use, in this case, if you have this problem, we're going to use a raster rendition. All right, so let's get the Euclidean distance that failed us for Great Wall and remove that and rerun it based on the raster. So here we go to our toolbox. We're going to utilize a distance. It's going to be Euclidean distance. Remember, Euclidean distance is straight line distance. So we're going to go to polyline, the TIFF, and the output cell size here should be going to 90. I'm not sure why it's not. So we want it to be 90. Let's make sure it's going to the right place. So yes, it is. So let's run it. And I'm going to pause the video here for a moment because this is probably going to take a couple minutes. Okay, that Euclidean distance turned out correct. You can see down towards the bottom here, I don't get that drop off. And it took about 1 minute to process. Okay, so there's our Euclidean distance. Now we just need to reclass it. So under our reclass, we need to go to our toolbox, we're going to go into reclassing. So here we're going to put in our Euclidean distance from the Great Wall and value. Go to classify, and we're going to be in 5 breaks. We can stick an equal interval. And our breaks in this case are going to be 2,000, and they're going to be 5,000, and then we're going to do 8,000, and then 10,000. Okay. So we're capturing a small part of the histogram based on our 2,000 to 10,000. But anything above 10,000 is completely unsuitable, so we're not going to worry about it. And we go ahead and say OK. And at this point, we're not going to reverse this actually. We're going to keep it exactly the same. So we want to be far away. I should just correct the statement that I just made. We want to be far away from the Great Wall. So here, instead of being far away is unsuitable, I'm correcting myself. We want to be far away. So from 10,000 up to the highest value, that's going to be very suitable. Okay, so we want it to be away from the Great Wall just because we don't want to see it. We don't want to have it be an industrial facility that's close to a historical asset for, especially for tourism. Okay, so we go ahead and let's rename this because this is important to rename this correctly. So this is going to be reclass, and this one is now going to be, we'll just call it Great for Great Wall, G-R-E-A-T. And I'm just going to make it capitalized so I can really see it well and say OK. All right, that looks pretty good, I think. Yeah. All right, so what we want to do now is zoom to layer, and let's go ahead and put a stretch on this. We're going to make green, and in this case, our 5s are going to be green. So we want to invert it again and say apply, OK. Yeah, that's what we want. So as we get far away, that's great. We want the greens. If we are close to the Great Wall, let's drop in the Great Wall polyline. That's going to be very unsuitable, very close to it. And these areas out here, this dark green, that's going to be considered suitable. Okay, so I took the Great Wall away there. I'm going to also take away the Euclidean distance, remove that. I'm going to take away the polyline. So what we have now is we have 3 of our 4 criteria. So we're getting very close. The last thing we need to do is actually calculate for slope. So slope's going to be a little bit different than the processes we've been doing so far. So far we've been working with Euclidean distance from things, and at this point we want to switch into doing slope. So slope's going to be different. So we're dealing here with raster values that are digital elevation, and we want to calculate based on those cells how steep an area is. It's not so much what the elevation is, but how much change in a downward slope or upward slope we have per pixel. So we're looking for these real flat areas, and we can kind of see them, where there are these kind of neutral, continuous values that don't change very much. Those are the places that are going to be highly suitable for this criteria. So let's go ahead and run slope. So slope's going to be under Spatial Analyst Tools, and it's going to be a surface tool, and it's down there at the bottom, slope. Our input raster is going to be SRTM, and we want to make sure that it's not in degree, that it's going to be in a percent rise, because we want to calculate this based on percent in this case. That's an easy way to understand slope and for suitability criteria. Importantly, we're already in meters, so we already have a projection system. It's a UTM projection system, so we're not going to have to correct for a Z factor. We can just leave it at 1. Okay, so let's run this and say okay. Runs pretty quickly. And there we go. So now once we have slope values, these areas that are really low, these greens, those are going to be the areas that are quite suitable because they're in relatively flat areas. And the facility here is assumingly pretty large, so we want a nice flat expanse area to actually place this. And then we also stay away from difficult terrain for construction and flooding issues and whatnot. So the criteria setup is based on a flat area. And to get to that suitability, we want to reclass this. And to do so, we want to, let me get my note here real quickly of what we want. Okay, I'm checking my break values here. So there's the break values. 0 to 2 is a 5. 2 to 4% is 4. 4 to 6% is 3. 6 to 8% is 2. And 8 and on up to the top value is 1. Okay, so we're going to go to reclass. And we're going to be reclassing this input. So it's going to be slope. And we'll go to classify. It's going to be 5 classes. So 5 classes, equal interval. And here we're going to do this as 0 to 2. Here, hang on one second. Let me make sure I have this right. So yeah, that's right. Okay. So it's going to be, let's go to classify. So instead of 9, it's going to be 5. I say okay. And I can actually do it out here since I can just say 0 to 2. 0 to 2 here, and then 2 to 4. 2 to 4. And then we're going to go 4 to 6. And then we're going to be 6 to 8. And the last one is going to be 8 to that top value. Okay. And importantly, I don't want to reverse it. Or actually, no, I do want to reverse it because I want to make sure that my 5s are going to be in that really low percentage. So I reverse those. And I'm having a problem here. I'm just going to pause the video and figure it out real quickly. Okay, I went back into equal interval and set these up. So here we are, 0 to 2 is a 5, and then 6 to 8 is a 2, and then 8 to the highest value is a 1. And we go ahead and say OK. And it runs it there. So let's go into our properties, and we're going to stretch this. So we're going to go up to here, and our high value is 5. And we'll say apply OK. And that's what we want. I want to make sure that's what we want. Yes. Okay, so that's correct, but you know what? I renamed this wrong. I'm just going to run through that whole process again because I'm not 100% positive I got it right. So I'm just going to remove this, and we're going to redo it. So we know that our slope is correct here. And I'm going to go back to our toolbox, and at this point I'm going to reclassify it. So I'm going to stick in slope, and I want to go into equal intervals, and not defined, I want equal, and 5. Okay, so here the first break is going to be 2, then it's going to be 4, then it's going to be 6, and then 8. Okay, and say OK. And again, let's make sure we have this right. 0 to 2 is what we really want. So we're going to reverse that. So it will be a 5. Okay, because 5s are highly suitable. And under my name, I want to make sure that I got this name correctly. So here I'm going to say reclass, and then I'm just going to capitalize slope. Okay, and run that. I'm going to go to stretched, and under high I need to invert it and say apply. Okay. Okay, great. That's what we want. And at this point I'm going to get rid of my original Euclidean distance, and now I have my 4 criteria for suitability ready to go for the final suitability. And we're going to run the final suitability 2 times. The first time is without any weights, and the second time is with weights. So let's go ahead and start this process. So what we're going to do is we can click on all these, and we're going to go into our toolbox, and what we're going to do is use map algebra to do this. So go to Raster Calculator, and under Raster Calculator we can now see all our reclasses. So we have these 4 reclasses. That was what we want. So the first equation is pretty straightforward. It's just adding these up. So the reclass is going to be slope, and then a plus, great, double click, plus, power lines, double click, plus, and then reclass wind. And let's call this, let's give it a name, let's call it add 4. ADD4. So we're adding up 4 layers, add 4, and say OK. Okay, now this is a mess. So what we want to do is go into, we're looking for our 20s. Those are the ones that are going to be the most suitable, because we're adding up 5 plus 5 plus 5 plus 5 across slope, great wall, power lines, and wind. So here we'll go back to properties, and let's do a stretched. And so in our 20s, we're going to invert it, say apply. Okay, anything that's a green up here at the top, let's take these guys off. So we can see these deep greens, those are the ones that are really highly suitable. And then these reds here are very unsuitable. The problem is that we have a lot up here that's considered pretty suitable. It's not getting a 20 because it's not on the distance from power lines. It's scoring very badly there. So it's not getting a full 20 up here. We can see where the full 20s are. They are relatively close to power line infrastructure. So let's do this. Let's weight this up a little bit, and we're going to get a little bit different portrait of our suitability, because right now it's factoring in everything equally. So in this case, what we're going to do is we'll keep add 4 there, and we're going to go back and do Raster Calculator, and this is the weighting. So this is what we call weighted linear combination, where we're actually giving a weight to each one of these variables coming into the system. So we just need to get our calculation here. I have it written down, so I'm just going to work off of it. The first one's wind, so we're going to put in wind, and that's going to be at 50%. So that's going to be times, so we're using a multiplier, times 0.5, and instead of just addition, we need to put this into a little container. There we go. Now we can go ahead and say plus, and now it's going to be the next one. So it's going to be plus power lines. Okay. Put this into, Okay, and we need to multiply this, use a multiplier, so it's going to be times 0.20 or 0.25, so that's for 25%. Then we'll go to plus. And actually need a little space between these. Okay, the next one's going to be the Great Wall at 12.5%. So we put in Great. And in the assignment, I may just put this equation in so you don't have to spend so much time on this. So here we're going to multiply it, and it's going to be 0.125, and put a space right here. Okay, and then plus. And then we're going to put in the last one, which is slope. And he's 12.5 also. Multiply it. 0.125. And let's call it something different now. So let's call it, we can call it weight, W-E-I-G-H-T, and say OK. It ran it, or it's running it. Okay, great. So there's our suitability, and let's go ahead and give it, so it's 1 to 5, which is great. So under properties, let's go to stretched and make it a color. So invert it to get greens for high and say apply OK. So it's giving us a similar pattern as before. So if we click on and on weights, we can see some differences. So with weight, it really takes care of this area up here and really sends that to unsuitable for certain areas up at the top. It also really makes certain areas down by Beijing highly unsuitable. And it looks like it increases the suitability maybe a little bit around the power lines in some areas. But we definitely get a different portrait than the first run. So, and it also looks like down here at the bottom with weights, it really brings the suitability even close to power lines down much further. Okay, so at this point in time, what we could do is we can get this ready for maybe a Boolean raster if you want to, or into some type of final map. And one final step here is, we don't have access to an attribute table. These are continuous values. If we want to bring this to an integer value, what we can do is we can go to math. And under math, what we can do is just use the tool int for integer. And we're going to input our values here. This is our constant values. We are going to put in weight. And maybe I'll just call this final instead of weight 1. So final, and say OK. And now I have integer values. And so now what I could do if I wanted to is reclass just for 5s, everything else go to no data. And we can see that those 5s are these little areas right here. We can see them, they're these light blue colors. So if we go to final, under properties, and stretch it out, say invert it, say apply, OK. You can see that real deep dark green color. Those are the areas that are considered to be highly suitable. So out of that whole process, at our very top rank, which is a 5, there's relatively speaking, not that much area that's actually suitable. and those would be the locations that we would go to first for actually siting this facility. Now under the attribute table, what we can do is we can look at the attribute table and we can see how many cells we actually have. So we'll get a count and we'll get a value. One thing to note here is that in the original materials from Tufts University, they see a count of 188.96 for a value of 5 and also 20. And we're having a slightly different value here at 192.89. Yours might be different also from either my number or their number. So this is approximately 8-acre difference. So given the space that we're dealing with here, that discrepancy I wouldn't consider to be significant, and it's probably coming from when we utilize a raster version of the polyline as opposed to the polyline itself for the distance that we derived. And then also we can check under our original 20 and see what that value was also. So here under 20, we can see that our 5s are 192.89 also. And you can see I've selected them here. So our 5 in our final run is the same as the 20. So 19 is pretty suitable too. So if we click on 19, we can see that we get a little bit more suitability. And if we go to 14, we can see that it's all kind of clustered around in the same location, which is it has to be, let's drop in some of our infrastructure here. I'll put power lines on top. See, it's got to be close to a power line. And if we go back to our original ranks here, we can see that power, first wind and then power at 25% in our final suitability was really important. And it's an important weight. So things that are close to that power line are going to score pretty high. So this is suitability. These are some of the tools that we use to do it. We can use map algebra. There's some other tools that we utilize for suitability also. But the ranking process at the end is we can either just simply bring in our criteria and add them up, or we can actually add a weight to them by adding in a percentage factor. And that's what we've done here. And so at this point, what we could do is we could go ahead and develop a final map. We could send all the values that we don't want to no data and then have a final value. We could then take that final value of 5 and send it to a polygon, calculate areas. We can do all kinds of things from there on in. But once we have this result, we've accomplished the suitability component of the processing.